Okay, so hope I'm audible and my screen is visible.
Yes, sir.
Okay, good. So good morning to all of you. So I'll be talking about recurrent neural network that you already are aware of. So before jumping into the recurrent neural network, let us try to quickly understand why we use neural network and what is the application domain and or what kind of problem can be addressed by neural network. So that just to give you a quick idea how we look into the different scenario. So typically when we try to solve any problem on computer, typically means that we want to do some kind of a automation, because we do not want to do certain jobs manually or on a regular basis. We want a machine to do that job for us. So so there are a lot of things that computer can do. So if you look into the problem space, that the kind of problem that can be solved on a machine or on a computer is pretty huge. We can solve a problem like sorting. If somebody gives you 1 million number, you know how to sort that large number. Then if you want to find out the shortest path on a graph, you also know how to do that. So these kind of problems are relatively easy, and you can develop polynomial time algorithm and you can solve it. So which is one class of problem. Then another class of problem, if you look like the game of chess, you can describe the problem in a formal manner, but the problem is that finding out the best move is not that easy. So you need a huge computation resource, but still the problem is you can describe the problem in a formal manner. The next thing is a set of problems, like if you want to identify a object on a given image, then the issue is you will not be able to describe the problem in a formal manner. When I'm saying the description of the problem in formal manner, that means, can I describe the problem mathematically? Like if I need to describe the problem of sorting mathematically, then I can say AI is less than AI plus 1 in a final outcome. So I can give some kind of a mathematical condition, and I'll be able to I'll be able to express that stuff. But identifying an object on a given image, I will not be able to describe, because but as a human being, I know how does that object look like, but describing that object in a formal manner is not that very straightforward. So typically neural network or machine learning algorithm are mostly used for this second category of problem, which are typically easy for common people but difficult for computer, even if you want to express. Then the obvious question is like, how do we solve this problem? Then that is the obvious question. So here what we do, we try to see a lot of examples, and by looking into a lot of examples, we try to find out the appropriate feature, and then we try to predict that stuff. So just to give you an example, so this is mathematically or in the mathematics domain, it is called the statistical inference, because if you look a lot of examples, probably you'll be able to say what would be the outcome for unknown examples that have been provided to you. So I usually give this example just to give some kind of an analogy with statistical inferencing. Like if you want to teach a kid the concept of color, so the thing here is you cannot describe the concept of color in a words. What do you mean by color? But every one of us can actually understand what does the color means, but we will not be able to express what is that color. And of course, to a kid, you cannot express like it is the RGB combination, because they will not know. Now what happens? Probably you will show a few red colored object to the kid and few other color objects also, and for every object you will try to provide some kind of a guidance, like it can be a red ball, it can be a red pen, it can be a red cube, it can be a blue ball, and so on and so forth. Now the kid initially will make a lot of mistake because the kid will try to understand the whole stuff is called the red. So, but the moment the kid learns the concept of color, he or she will be able to predict it correctly. And the thing that the kid actually learns, that the object property has to be thrown out, the whether it's a pen or it is a cube or it is a sphere or something else, that object property has to be thrown out. Some other property has to be taken when somebody is asking for some color. So this is kind of a statistical inferencing. We go through this kind of steps in many scenarios. So it's not only the color. If you think for the taste, like whether something is salty or something is sweet, we also go this kind of steps knowingly or unknowingly. So this neural network, the idea of neural network is to try to identify the set of features itself. And the moment it identifies the feature itself, then it will be able to predict more accurately. So that is the main intuition behind this neural network stuff. So typically, so in this lecture or in a neural network domain, they will be mostly following, or they will be looking primarily this category of problems. So with that background, I will go into a particular class of problem which probably requires the recurrent neural network. So so if you look into the problem space of that second category, where we cannot describe the problem in a mathematical manner, but we would like to apply a neural network, then in that domain there are a lot of other kinds of problem as well. So it can be a problem where where some image has been given and I want to classify what kind of image it is. So this can be one option, or I can have a text that I want to specify, or something like I have written one example like this. In 2017, I went to Bhutan. So, and I can ask some kind of a question in which year I went to Bhutan. So it can be some kind of a text stuff that I have to predict. You can think of stock market, like you may have to predict uh, the stock value for a particular company. So there are various kinds of problems, and if you look into these three problems, for example, this is an image, this is normal text, and this is some kind of a real values that we want to predict. Now among these three, this kind of problem, when we look into an single image, then it is mostly static. I have a static information and I want to classify. The problem with this text and the stock prediction is that it will have some kind of a nature, it will have some kind of an effect from the past data. Because if I, so for example, for text, if I specify only this thing, and if I want to predict Bhutan, then probably Bhutan has some kind of a correlation with the previous stuff. Or it can be Bhutan, it can be something else also, but the word can have some kind of a influence from the past words. Similarly, in the stock market, it's heavily dependent on the past stock values. Not only on the past stock values, there are many other factors as well. So these two problems at least have some kind of a sequential relation among the inputs. So when we have this sequential nature, then in general, or in many cases, it has been observed that the plain deep feed-forward network does not work well because of many issues. So deep neural network, or maybe deep feed-forward neural network, does not work well in that kind of environment in many cases that people have observed. So we need to have some model where we can actually express the sequential nature. For example, the thing, if you look into these two examples, I went to Bhutan in 2017, or in 2017 I went to Bhutan. Now these two statements have the same information. Now if I ask when did I go to Bhutan, then in the first case the last word has to be selected for the answer, and if you have the knowledge in the second sentence form, then the second word has to be selected as an answer. Now if you have a deep feed forward network, something like this, then sometimes you will be choosing the last word. That means 1 2 3 4 5 1 2 3 4 5 6. So in the first case you will be choosing the sixth word, and in the second sentence you will be choosing the second word, so which will be somewhat difficult because the ordering of the sentence will actually matter. Because when we answer certain queries, we first read the sentence, we understand, and then we speak. So in this case, the problem will come because sometimes you have to choose the second word, sometimes you have to choose the sixth word, so which can create some kind of a problem. So in order to overcome this kind of situation, people also propose a methodology called bag of words. So what is the idea? In the bag of words, they try to find out how many times a word is actually appearing. So that means if you look into these two sentences, then each word actually appear only once. Now, if I remove that sequential nature, then probably if I have the bag of words modeling, I'll be able to predict it correctly, because only thing I have to select the number and I have to answer. But even if I have bag of words, it has some kind of a problem, because let's say there is a sentence something like this: the mouse chase the rat. So this is one sentence, and let's say the other sentence is the cat chased the, sorry, I made a mistake. So this is cat, the cat chased the mouse. Now if you look into these two sentences, then the bag of words will have the same modeling, because each word actually appears only once, except I can ignore the probably, but the important stuff is each word actually appears only once. So bag of words will have the same modeling, and eventually I will lead to a problem. So because the meaning will get changed. And there are other issue. If you look into this second problem, like I grew up in Bengal, then I have certain texts and then I have to predict this word. I can speak fluent, probably Bengali, because this word has some kind of a influence from the past data. So it can be a dependence. The dependency can come from a long distance, not like a very short distance. So in order to model all of those things, we require actually recurrent neural network, or maybe we can say in this way that recurrent neural network have found to be perform well in order to address this kind of issues, because it tries to model the sequential nature in the given data. So, and the type of applications that we have, if you look into, then feed forward network, which is the simplest model that we have. So here you give some input, like you can give an image, and the you will probably classify what kind of image it is. Then if you look into an image captioning problem, it's pretty interesting in the sense I have a static input, but I have multiple outputs. Because for an image, if I try to give caption, I can express the caption in multiple ways. So I can have uh, in many ways I can actually express, and each word can be treated as an output. So it will be kind of a sequence of words. So the upper green circles basically denotes each word that we are producing as an output. Sentiment analysis, like you are getting a text which is a sequence of words, and then you try to predict only single outcome, whether it is uh, positive sentiment or it's kind of a negative sentiment. If you want to do a video frame labeling, probably you have to take each of those frames, and for each frame you have to give some kind of an output. So there are many combinations, and many complex combinations can come. Like if you go for machine translation, like you read in English and you try to generate Tamil. So you will be going through the whole set of inputs, set of English words, and then you'll be generating a sequence of Tamil words. So there are many such variant of this thing. So on the feed forward network, the first diagram, that is typically used for when we do not have sequence. But for the remaining scenarios like video frame labeling, image captioning, and other stuff, we use the recurrent neural network because it has some kind of a sequential stuff within it. So let us look up very simple example for RNN, and we'll be formalizing on top of that. So in a very simple situation, let's say I get a character, which is my input, and I want to predict the next character. So this is a very simple problem because I would like to predict the word itself. So I am just predicting each and every character. For example, here, this example is for with respect to hello. So if somebody gives me age, then this age needs to be modeled first. So here we are using one hot encoding. And since we have 4 characters here, so we are representing using 4 tuple. And if the first position basically indicates whether it is H or not. So I have H, and I give it to a neural network for the time being, and it will predict the probability of whether I'm going to get an H or E or L or O. So these 4 characters that we are trying to model, basically this set of characters. Now once we have this H, which we have encoded as one hot encoding, we give it to neural network. How we are getting that step, I will explain. And this block will predict the probability for each of those characters, so which has been listed here in the output layer. Now here, so in this example, so it predicts the second character with maximum probability. It's not the real probability, with unnormalized probability, and probably we can say that it's predicting E correctly. And then, so we are predicting for the first time step 1. In time step 2, I will get an E. I have to predict the next character. Again, I will do the same thing, and I will get some kind of a output here also. Now, in this case, if you see, then this character will have the highest probability. So effectively, it will predict O, but we are expecting L. So there is a mismatch, and we have to adjust accordingly, because when we go for supervised learning, we predict something. If we mispredict certain things, then we readjust the weight. So depending on that step, we have to readjust the thing. And similarly for the other time points as well. Now, interesting thing here is that the network, so when we are predicting for, let's say, time step 1, we have some kind of a weight parameters here. We have some kind of a weight parameters here. And in the hidden layer, also there will be some kind of a weight parameters, which is not visible for the first time step, but you can see that there will be some weight parameters when you go for the second time step. So effectively, there are some weight parameter also here. Let me distinguish this by with some other thing, otherwise it will be confusing. I will be saying all W. So we have parameter W1, W2, and W3. In the second time step, also I have one W here, another W here, another W here. So, and interesting thing here is that this, let me call this as W4. Now W1 and W4 will be the same. And if I say this is W5, then W2 will be equal to W5. That means I'll be reusing the same set of weight parameters. So here I have written only this thing. So these parameters will be same in every place. Similarly, this weight parameter will be used here, similarly here, and again at this point of time. And this WHH will also be used here, also be used here, and also be used here. So the thing is, we here, if you look into the stuff, so when I got H, I calculate, I predict the next character. Along with that, I also provide some additional information, or I modify the internal state. So initially I have a state something like this. The moment I get H, I modify the internal state. So I remember some kind of a past history. So if you look into this layer, at every time step, the state is getting changed. And if the state is changed, if I get a different input, probably I will predict the next character in a different way. So effectively, it will be modeling some kind of a sequence nature, and then it will actually predict the correct character. And the most important thing is the parameters are shared across the layer, at least when I unfold the new recurrent neural network. So I can view this the whole recurrent neural network as a unfolded over time. Now, if I try to combine all those things, then probably I end up with this kind of a diagram. And if we unfold this figure, then I end up with the diagram that I have elaborated here. So in a concise form, we have some input, we have some parameters which will be shared across the time step. We have the hidden layer, and this parameter will also be shared across the time step. We have this parameter which maps the hidden to the output. That parameters also be shared. So effectively, it will be a very, very concise representation of the actual model. So typically, if you look into CNN or deep feed-forward network, you will have a lot of parameters. But in case of RNN, the parameter can be reduced because it uses the same set of parameters for every step. And since it has less number of parameters, in many cases, it has been observed that RNN can learn from a very limited set of examples. For normal feed-forward network or the CNN architecture, you may require a lot of examples to learn. So which is the advantage of RNN? So, so if we try to elaborate more formally, so it's basically represent some kind of a computation. For example, when I have a recursive definition or the recurrence relation, we can actually express in a similar manner. For example, let's say I consider this system. So I have a state and I have a set of parameters which basically determines the next state. If you remember the past example, we had the state, this green is the state, and we use a different set of W parameters, and then we predict the final output. So it is that thing. For in this case, we do not have explicit input. So over the time, it is getting changed based on some parameters. So this is the basic form of the recurrence, and for a finite number of steps, we can actually unfold, and if we unfold, we can express the stuff in this manner. And more pictorially, like we have some initial state and we apply this function, we reach to a next state. Again, we apply this operation, we reach to this state, and so on and so forth. So it's simple unfolding of the stuff over time and applying this function operation. So this is the very, very basic form of recurrence, and it does not have any input as such. Now, if you have this input, then you can actually extend the idea in a more formal manner. So we can express in this manner. So a current state will be a function of the past information, the present input, and the set of parameters. And you can actually unfold in the similar manner. So you can write a more recursive definition stuff. So effectively, what actually happens, like if you want to look into HT, what is the current state at time step t, then it effectively depends on all the past inputs. Because when I get some input, I modify my state. So effectively, I'll be storing some information of the past inputs into my states. So if I can store the relevant information, then probably I'll be very happy and I'll be able to have the best model. So this kind of scenario can be modeled in the succinct manner in this way. I have input and I have a feedback loop in the hidden layer. So if I unfold over time, I end up with a diagram something like this, and on this diagram we can do analysis and we can understand more easily. The important thing here is that all of these operations are the same. So this F operation means the set of weight parameters will remain the same. So there will be some kind of a weight parameter also. The same weight parameter will be at every time step. So, so the thing is, just to summarize the stuff. So if you do this unfolding of this recurrence relation, then you end up with a more complex function, and which we can actually express in a very, very concise form. So unfolding the process has some kind of an advantage. So because we'll be able to visualize certain things, how the system is evolving. And one of the major thing is that the parameters will be shared. We use the same transition function with the same parameters at every time steps. So which is one of the advantage thing. And I have already told that it can be trained with fewer example, and it's a very, very concise representation. This unfolding of the stuff will basically provide us more in-depth information. So if we want to really understand or how certain things are happening, we can unfold and we can actually visualize how it is actually working. So this is just an example when I have input and with along with the output. So this is the diagram that we have seen with the character stuff, the prediction of the next character thing. So in a more formal manner here. So here you can see that we have this W parameter, we have this U, we have V, and if we unfold the stuff, we will have the same set of parameters. That is one thing. Second thing is that we have input, it goes through the state, then it probably predicts certain kind of an output, and we have the target output also. Now, if we have these two things, we can compute the loss. Similarly, so this is in the first time step, this is in the second time step, we have some loss. This is in the third time step, we have some kind of a loss also. Now, just to understand few things, like I am assuming that all of you are familiar with the backpropagation algorithm. Now, if you consider only this network, on the network that I have unfolded for 3 time step, and this is the network. And on this network, if somebody asks me to do backpropagation, I'll be able to do, because there is no loop here. Because since we have unfolded the thing, there is no loop, and we can do the backpropagation in the same manner. Only concern here is, like, we have the same set of parameters. So in order to elaborate, like say, if I make this parameter for the time being different, so this is in the first time step, this is in the second time step, this is in the third time step, and so on and so forth. Now, if I make this set of parameters different, then it boils down to a normal feed-forward network, and you will be able to run the backpropagation algorithm, because every time you have to find out dl by del w, 1 or 2 or 3, whatever may be the parameter. So that was the thing that you have to found it out. Similarly for the other parameter also. Now, so if I unfold and if we rename the parameters, then I can apply the backpropagation algorithm easily, or the whatever knowledge we have, we can actually apply that stuff. In this case, the problem here is that all these wi's are the same, or all the vi's are the same, all ui's are the same, and we have to consider the total loss. So I have loss for every time step, and I need to find out the total loss. So effectively, my loss will be computed as loss over all the time step. So that will be my total loss, based on which I have to compute. And we can compute the gradient in this manner, and we can compute the gradient in this manner, but we have to finally combine certain things, because we do not have explicit W1, W2, and W3. So if I really want to find out del L by del W, then it will be the summation of del L by all Wi for all time step. So that was the basic idea for to apply backpropagation on this kind of network. So which is known as BPTT, backpropagation through time. So I have some more slides, I will elaborate. But since this diagram is used for to elaborate that stuff, I have already elaborated the thing. So we will be applying backpropagation, but it's a little bit variant. So it will be backpropagation through time. And there can be many other kind of variants also. Like earlier we have seen a feedback loop here. Now the feedback loop is from output to the input. So if we unfold this kind of diagram, then I end up with this kind of architecture. Now, if you try to train this kind of model, then there are certain interesting fact you may remember. Like so here what happens, you are getting feedback from the output. Now when you deploy this model in practice, then you get some input, you predict the output, and that output will go into the next level, which is shown through this edge. And you can keep on doing so, which is fine. But in case of training, you have to use a different thing. The reason is as follows, because when you are doing this training, so if you are doing this training, you are giving this input, you will be predicting something. And this prediction can be a wrong prediction. But you have the correct level available to you. So during the training, what you have to do, you have to pass this information in the next layer. Because when you are training, if you give wrong information, to the next layer, then it will not learn. But during testing, you have to pass whatever you are predicting. But during the training, you have to ensure that the correct level goes into the next level. So there are this kind of tricks that you have to apply, and you have to make more logical stuff. This is again for a sequence processing, which I think I have elaborated earlier, like for sentiment analysis. So you keep on looking the stuff, you read the whole set of words, and then you find out the loss, and then you do the backpropagation. So in a more formal manner, how does a recurrent neural network looks like is as follows. So this is the main activity stuff. I have this input, I transform it with some kind of a matrix, and then we store it in the hidden state. So in this neuron, the first thing is that we do some kind of a linear combination. So linear combination of inputs and the past state information, and with some kind of a bias. The second step is that whatever we are getting as a pre-activation value, we apply some kind of a nonlinear transformation, which is tan H, and it is typically used in case of recurrent neural network. So this HT will be the new hidden state, and based on this hidden state, we can do this transformation and we can get the final O. And so that will be O, and if I want to predict, so O will be a set of values, and if I want to predict a single character or certain things, maybe we have to take the softmax in order to make the final prediction. So here, so in this example, we have shown that the input and output have the same length, and recurrent neural network has the advantage also that it can handle variable length input. Like if you have CNN architecture, if you give an image of say size 10 cross 10, which has been developed with an input size 10 cross 10, now if you give an image of size 40 cross 40, it will be a problematic. There will be kind of an error because of the shape mismatch. But in case of recurrent neural network, you can actually handle the variable length also, so which is another positive side of the recurrent neural network. And when you have this variable length, you may have to append with some kind of a additional string which will indicate the end of input. So which is good thing to model few of the cases. Now coming to this backpropagation through time that I have already elaborated. So if we try to find out the gradient, then we have to unfold. We have to decide how many steps we want to unfold. So typically, so you are getting an input sequence. The moment you hit the end of sequence, then you start. Then you can actually activate the backpropagation. So let's say I am getting a sentence which has 6 words. So each word I can think of input at every time step. So I will go through the whole sequence. Then I will start applying the backpropagation. So it will get unfolded 6 times. If I have a sentence with 10 words, then it will get unfolded 10 times, and then the backpropagation will actually take place. Now, one of the major issue that we will face is the vanishing gradient and exploding gradients, because here we have the same set of weight parameters, and that will get actually multiplied over the layers when we are trying to compute the gradient. Now, if these values are greater than 1, and if you have 100 layers, then you can assume that the value will be too high, and if it is less than 1, then value will be close to 0. So that kind of problem we usually face in the recurrent neural network. Now, in order to compute this thing, so what I have told earlier, that we have to compute the loss for every time step and for all such outputs. So this k is the output at a given time step, and we are summing over all the time steps, so that tau is the length of the sequence which we are unfolding. So we can write, so the first statement is for with mean square error, the second with the cross entropy, so which can be used in the similar manner. Now the basic equations that we have is the ht and the yt, which basically use some kind of this nonlinear transformation. So if we try to find out the gradient, so the loss, so you can see this loss, the total loss that you want to compute, and with respect to W. So effectively, we have to sum the loss for all time step. And then we can actually unfold the thing. So in order to compute the gradient of E with respect to W, we can apply the chain rule that all of you are familiar with. So it will be YT first, and then we can determine from HT, and then HT to HK some level, and finally HK to W. So this is nothing but the chain rule that we can actually apply. And interesting thing that you can actually show that del HT by del HK will be have this kind of expression. So I will not elaborate much. So this will be some kind of a matrix which can be expressed in kind of a diagonal manner, because W is common always. Now, if your if your eigenvalues, the diagonal matrix basically consists of those eigenvalues. If the eigenvalues are greater than 1, then your gradient will explode, and if the gradient is less than 1, then your gradient will actually vanish. So if there is an explosion on the gradient, we can handle the situation more comfortably by clipping the gradient. But in case of vanishing gradient, it's pretty difficult because we do not know what to use. And this is a kind of a mathematical expression using which you can actually show that it can go into vanishing or the explosion side. So in order to overcome the vanishing gradient, what people have proposed is to allow some variant in the vanilla neural network. So this neural network that we have seen till now is called the vanilla RNN. Now on that vanilla RNN, we add additional control. So here we have added 3 additional control, which basically says the first one, it gives some kind of an indication whether to propagate the input or not. So this is called the input gate. Then there is some flexibility to forget the past information. And then again, you have another control on the output side as well. So if you look into this side, then this is the simple RNN. On top of that, we are adding this additional feature, and we are trying to control the propagation of information. So if we have that additional stuff, we can control the functionality of recurrent neural network more meaningfully. So this is called long short time memory, or in short, it is called the LSTM. So I will not elaborate much because we do not have much time, but this is the basic idea on top of the vanilla neural network. And this methodology can be expressed with more mathematical expression. So when you have these gates, typically they use the sigmoid, and on the activation, it will use the tanh typically. And if you, so there are many variant of this diagram. So here's just one of the possible way. Now, if you look into over the multiple steps, then the information will propagate in this manner. Now, now how it can actually help the vanishing gradient, like when you compute some gradient, it will get propagated in this path. Now, if this gate actually allows to propagate the information in this direction without any restriction, then you, whatever gradient you compute at the output, you'll be able to propagate it across the network. Because these additional gates that you have uh, on the on top of the vanilla RNN, it basically, if your parameters are learned properly, then it can propagate that gradient pretty easily. So there is a chance it still you can have vanishing gradient also, but there is a chance that it will not face that kind of issue. So with this, I'll summarize the whole thing. So RNN are good to model the sequence. It can handle the variable input length, and most importantly, the parameter sharing. So it's typically very concise in nature, and it will have a very succinct information. And in order to train the network, we use a variant of backpropagation through time strategy and LSTM, and there are other kind of networks like gated recurrent unit, which are actually used to overcome the drawbacks of the vanilla RNN. And you can propose a lot of interesting architecture on top of that. So with this, I will stop. So I'll be happy to take few questions.
Thank you very much, Professor. Actually, it was a very nice talk, quite interesting, and you covered the basics so that even you started from the basics so that even people with a little background of the RNN can also follow. I hope it was quite interesting for the audience. Um, any questions from the audience? Please, if you have any questions, you can drop in the chat box also, so that we'll be able to take it up. In case you don't have any questions immediately, I hope Dr. Arijit won't mind in emailing him. Arijit sir, they can contact you later also, right?
Yes, absolutely. Not an issue. I'll be happy to answer if you have any kind of questions or any other thing. So I have given my email ID also.
Yeah, Suresh Kumar has raised a hand. Can we unmute Suresh Kumar so that he can ask his queries?
Hello, sir.
Yes.
Sir, I mentioned a couple of questions in the chat box. Could you please look into?
I cannot see in the chat box.
So these are gone. This question has gone to ITM Sri Shiti Chittur. Okay, let me everyone. Okay.
Yeah.
I'll please see now.
Okay, just give me a second. Let me read out because it's a very big question I sense. Suresh Kumar. LSTM based modeling is pretty successful for text generation, say summary generation, but what are the state of art approaches for text generation task? Or just LSTM will do? Of course, LSTM will not do. You have to take a lot of other thing into account, and you can look into the attention architecture and many other bidirectional, many other things. So I generally do not work on the NLP side. So I'm not very much familiar with other kind of architecture. So it will be better if you can explore, but simple LSTM will not do, definitely. Uh, the purpose of saying LSTM just to give you the basic idea. Then for text generation, could you please tell us when to use LSTM and when to use by LSTM? So see, if you have if you have some kind of a dependency in a way, like if you want to predict the first word by looking into the set of words that are given in the towards the end, so you have to analyze the situation, how the dependencies are related. So if you can analyze that stuff, then probably it will be easy for you to select whether to use LSTM or the by LSTM. Among LSTM's encoder decoder based modeling, transformer GANs, which is most promising for a domain specific generation, assume domain is small. This is a very open ended question. It depends on the domain. So nobody have any idea which model will work best for what kind of environment. So typically, if you have sequence, we use RNN based architecture. That is the main thing. So there is no answer for that. So up to what length LSTM based text generation is promising? I have no idea, in the sense like you have to experiment. It depends how you are actually modeling your stuff, because if I model my text or if I model my word as a one hot encoding, I can have certain things. If I use the word embedding stuff, I can probably make more meaningful model, and probably I can go for a higher depth also. So you have to check that way. So what is the difference between softmax and hierarchical softmax? What can be the use case of each of them? So what do you mean by hierarchical softmax? I do not get. Uh, so probably I will not be able to answer this question. So if I assume this hierarchical softmax means you are taking it, probably it can go into the max pooling kind of stuff. I'm not very sure, but if that is the case, then I'm pretty sure that you'll be able to analyze yourself that how it is different.
Okay, I think that's all for the session. Thank you so much. Yeah, I think one more question is there, Alisa.
Can you please tell me the all unsupervised learning algorithm in deep learning? Please, can you please tell me the all unsupervised learning algos in deep learning? So unsupervised learning, there are a lot of techniques like k-mean clustering, then autoencoder, you can use PCA, you can use restricted Boltzmann's machines, and all sorts of stuff. So I'm assuming that you are asking what is the technique to do for unsupervised learning. What is the major shortcoming of LSTM? So LSTM has an issue. It's a pretty heavy network because you are adding a lot of additional thing. So it can consume a lot of memory and a lot of parameters will be introduced. So it's pretty heavy in the sense. So many times people have observed that they use the GRU, gated recurrent neural network, which sometimes help to overcome that computation thing, but achieving the similar kind of outcome. In case of time series domain, we pass a sequence of frames to LSTM layers. How the LSTM learns if we pass image at a time. So it can learn, like if you want to do a video frame labeling or video captioning or video to some description generation, then you have to do the similar stuff. Only thing, instead of a single image, you will be giving a different image at every time step. Typically, the CNN architecture, that can analyze a single image. If you have multiple images, then you have to replicate that step multiple times. So if you try to process some video, then probably a combination of CNN and LSTM, or more so the RNN, has to be used.